Okay, for classwork 1.4, the first thing is going back to this issue of notation. And the first few problems are what we've done already, just to kind of review what the notation is asking you to do. For number 1, I need to find f with 6 plugged into its x-coordinate. So I find the function that is named f, and wherever I see the variable, I put a parentheses, and I'm going to literally just take whoever is there and put it in. For number 2, when I move over to g, I look at the g of x function up here, and it says it is 2x plus 5. So I'm going to write 2 times parentheses plus 5. Everywhere that the x variable is, I put a parentheses. And then I am going to take whatever's inside and plug it in. With simplifying, you need to know when you can simplify and when you cannot simplify. If you have addition and you do not have the exact same variable for each of the individual items being added, you cannot add them together. You're just stuck with it. That's a done deal. You cannot simplify that any further. So the answer is literally just the 2b squared plus 5. And then for number 3, I'm turning to the h function. The h function has the variable written twice. So what I'm going to do is I'm going to say x squared is changing to parentheses squared plus, and then 3 times x is going to be 3 times parentheses, and then the minus 10. I left a parentheses everywhere that the variable was located, and now I'm going to take -1 and put it inside of every one of those parentheses. Then doing the arithmetic, when I square -1, I'm multiplying -1 twice, giving me +1. 3 times -1, and then the minus 10, and that ends up giving me -12 altogether. So that was just reminding you, taking you through the notation and what it is asking you to do. Now I'm going to move over to this next bunch is called function composition. Now, when you have a pair of functions, I'm going to erase a little bit. So let's say I just have these two functions. I could add the two functions together. I could subtract the two functions. I could multiply the two functions. I could divide the two functions. Those are your 4 operations that you're used to dealing with. If I were to add them together, for example, if I said, I want you to find f of x plus g of x, then you would write each of them down. This plus sign stays a plus sign between them. -2x plus 2x is 0, and I end up getting 5. So you can do operations with a pair of functions. That's addition. And what I'm going to do is next show you multiplication just to make sure you're clear about some things before I move on to what function composition is. If I'm multiplying them together, then I want to make sure to put a parentheses around them. Because you want to notice that because you have an addition there with the 2x plus 5, you need to bring a certain property into play. If I needed to multiply those two functions together, I would need to take the multiplication of the singleton term negative 2x and distribute the multiplication over the addition. And that would give me negative 4x squared minus 10x. So I can add functions together, I can multiply functions together, and I'm not going to go over subtract and divide because it's pretty similar. But with function composition, you're doing a different type of operation that you're not used to doing. I like to call it plugging in, plugging a function into another function. The notation that is being used here is actually nicely descriptive. If you look back at what these were telling you to do, this said to take the function f, and everywhere you see the variable, replace it with a 6. This is telling you to take the function f, and everywhere you see an x, you're going to substitute a big, giant formula.
So, Ms. Blanchard, this why
I'm
a bit confused on it, because wouldn't it just be negative 2 times 2x plus 5? Because you wouldn't put negative 2x since g of x already replaces that variable, right?
Oh, wait, you're saying the answer to the Oh, you're doing this problem.
Yes.
Okay. You know what? Let me write it out, and then I need to hear your question a second time after I write it out and see if we're thinking on the same wavelength. With f of g of x, one thing you could do is you could write in the g of x formula right here. You don't have to, but if you're doing a slower step-by-step process, that might be what you need to do. And I'm sorry if I didn't answer your question. It's just I need to make sure I'm clear on what you're saying, and I almost have to write this out first and then hear what you're saying. Now, the f function is the one that's having something plugged into its x. The f of x function is negative 2 times its input. And so its input is 2x plus 5. And I think this is what you were saying. I'm pretty sure this is exactly what you said.
Yeah.
So yeah, you got it. Now, realize that once you have plugged in or substituted in and gotten to this point, you're done with the notation. You want to then just step back and look at what that is telling you. And this is telling you you're multiplying negative 2 by parentheses 2x plus 5. So you're distributing the multiplication of the negative 2. Mm-hmm.
the reason why I said that before is because you wrote something different up there. I just made
Ah, you know what?
okay.
Yes, let me clarify what I did differently here. Here it said to multiply. And when I multiplied, I just wrote the two functions as they were written side by side and put a multiplication symbol. And then I did the math with what I had. And what I had was I need to multiply a negative 2x over this parentheses. And it's really important to understand how this is different from what this is telling you to do. With this, it's telling you to replace the x variable with whatever this g of x expression is. And that turned out to be a very different answer. The fact that you had to distribute multiplication over addition was the same. But that was more coincidence than anything. So I'm just trying to make sure you're understanding the difference between what this notation is asking you to do versus what does it mean if it's asking you to add them? What does it mean if it's asking you to multiply them? Okay, let's look at the next one. What I'm going to do is I'm going to write h of, and then I'm going to go all the way inside and look at what's there. G of negative 1. I want you to think about it. Do you think you know what you need to do? I'm going to bring this down where we can see everything we're working with. And now I'm going to point out we're dealing with h of x, but here it's g of negative 1. If you want to, you could, over on the side, just figure out what is g of negative 1 and then put it in here. Sometimes it helps to break up a problem into smaller steps. What I'm going to do is I'm going to make a bigger parentheses. And then I'm going to look at g of, and whenever I'm plugging something into a function, I'm going to replace its x with a parentheses. So g of negative 1 is 2 times x plus 5. And then I plug that negative 1 into the x input spot. And I want to say again, you may want to not do it all together at once. So what you could do instead is just take that g of negative 1, and I'm going to bring it over here. And go g of negative 1 equals 2 times x plus 5, put the negative 1 in, find what that is, it's 3, and then go to h and plug 3 in. You want to find the approach that makes the most sense to you. Some people find it easier to break it up into a smaller problem and then bring that smaller problem back in. At this point, you now are looking at h of 3. So you find the h function, and the h function is x squared plus 3 times x minus 10. I'm going to erase this. And then you're going to replace every x with a 3. And then that's going to give you 9 plus 9 minus 10, which would then be, I believe, 8. Yes, 8. Some things to notice. In number 4, you were having the x variable at the very center of all of this. For number 5, you had a number at the center of all of this. When you have a number at the center, you're plugging that number into one function and then taking that result and plugging it into the next function. But when you are doing function composition based on an x variable, you're taking the entire function and substituting that entire function in where its x is existing. Now let's try number 6. I'm going to erase this over here. And I actually should rewrite, yeah, all of it. Okay, h of f of x. If you can do what I'm about to do in fewer steps, feel free to. What I'm going to do is start with what's on the outside and just write it down. And realize that what it's telling me is to find the function f of x and plug it into the h. If I go slowly, I'm going to first identify what is f of x. And I look over and I find out, okay, f of x is negative 2x. So I can literally just replace f of x, and I forgot to put the x. So I can replace f of x with its formula right there in that expression. Then I'm going to look for h. Here's h. And if I have something in a parentheses after it, it's saying to plug it in or substitute it into the variable. So when I read h of x, I'm looking at it as h of parentheses is parentheses squared plus 3 times parentheses minus 10. So I'm rewriting the h expression, but instead of writing x, I'm putting a parentheses as an empty spot, and x is replaced with this expression, negative 2x. And this is as simplified as you can get because we can't add together terms that are not like having the same variable. Okay, now I'm going to go over to my typed version, and with function composition, this is the note that I wanted to make sure that you were clear on. It's an operation between two functions. One function is substituted into the variable of the other function, and it replaces. Okay. Now, I know that we're going to need to practice this. Is there anything that I in the, are there any questions I haven't answered that were thrown out on chat? I'm trying to look at it. I think we're good. Okay. All right. Are you ready? Now we move on to the next topic. You're going to need to learn a strategy for solving an equation in the format of what you see in front of you. The only types of equations we have solved so far are equations where there's one x sitting around in the middle of a function and we have to isolate it. Or if I have a quadratic expression and I set it equal to 0, I factor and I solve for what makes the factors equal to 0. This is different. I want you to take a look at, you have 9 to the power of 3x minus 1 must equal 9 to the power of x plus 5. Anyone think they know what you should do? Because you might actually just see it. Notice that you have the same number 9. What do you think you should do?
Get rid of both.
Mm-hmm. Right. And if you get rid of both, yep, as if the 9 wasn't there, the exponent on the left and the exponent on the right are now set equal to each other. And this is prepping you for something that's going to be coming later. Later, you're going to have to get to the point where you make these bases the same. But I'm starting you off with, once you see that you have the same number as a base, you can put the exponents equal to each other. Completely legitimate move. Then go forward with the algebra you know. The x is located in more than one position, but I can bring those together. I have 10 minutes left. Are you kidding me? I can subtract the x to both sides. And then I have a two-step equation. Add 1, and then divide by 2. For number 8, you have the same situation. These base numbers are the same. So you can just take the exponents and set them equal. And you want to recognize that you have a quadratic equation. You have an x squared term, an x term, and a constant. You want to make one side equal to 0. I'm going to subtract x and subtract 30 so that the right side now has nothing left. And then I'm going to factor. And I know some of you probably need a review on factoring, and we are going to do that before you have to test on factoring. Right now, I'm just going to throw it out there. Some of you remember, some of you don't, and I understand that. Once you factor it, you set each factor equal to 0. And we get 2 solutions.
Where did you get that?
So that's an issue of remembering how to factor, and I've got to be careful with my time at this moment. I'm before you have to test going from one to the other, I'm going to remind you of factoring. And I'll go ahead and just kind of remind you real quick. Do you remember that if you have x squared plus bx plus c and you want to factor it, you can start off with the diamond. And actually, I'll put an A here. With the diamond, you do A times C and B, and then you're looking for two numbers. These two numbers, when they multiply, they make the top of the diamond. When they add, they make the bottom of the diamond. So with this expression, my A is 1, my C is negative 30, 1 times negative 30, and then my middle X is being multiplied by a negative 1. And then it's a matter of sifting through your thoughts of various numbers that multiply to make negative 30 until you come up with negative 6 times 5 will give me negative 30, but also adding them will give me negative 1. And then that's how we determine those factors. And I'll spend time on that. I need to make sure to get through your exponent rules with you. And I've got 2 minutes. So you need to make sure you get the ideas here. You may already know this. And if you stayed through the beginning of lunch, you can get a little bit more out of this. I want to make sure that you understand these 3, or actually, no, 4, these 4 rules. You're going to have to spend some asynchronous time, either stay through lunch or watch the recording later. If I am multiplying 2 things together and they have the same base, look at what that means. If I multiply x 5 times, that is x to the 5th. If I multiply x 2 times, that is x squared. If I am multiplying, I want you to look at the way that's written and see visually why you add the 5 and the 2. The 5 tells me how many times I multiply x the first time. The 2 tells me how many times I multiply x the second time, and altogether I am multiplying. So the product rule for exponents is x to the a power times x to the b power is equal to x to the a plus b power. And have you seen that rule before? Then when it comes to a quotient, if you take a look at the picture, you can see that you've got a cancellation. You were multiplying by 5x's, but you're taking away 2 of them because you're dividing by 2 of them. And you're taking away 2 of them is the rule. If you have x to the a power divided by x to the b power, then you subtract the exponents. And it has to be in the order of the numerator exponent minus the denominator exponent. Now, for negative exponents, if we use the rule, or if we look at what this is showing, you should see that you get the cancellation just like we saw a moment ago. But if you cancel something out, you still have a times 1 sitting around. The rule we just used, the rule we just learned, the quotient rule we just learned, says subtract the exponents, 2 minus 5. This rule is going to take getting used to. And the rule is if you have a negative exponent, that means reciprocal. And by the way, this is why we use the -1 as notation for inverse, but unfortunately, that only applies in this specific situation. And then the next rule is the 0 exponent. If I look at what is the meaning of x squared divided by x squared, you should see, well, that's just 1. They cancel each other out. You get 1. According to the quotient rule, I subtract the exponents, so I have 2 minus 2 as my exponent. So the 0 rule for exponents is anything with a 0 exponent is simply 1 every time. You're going to be using these 4 rules a lot. So make sure that you study them, but study them by understanding them. If you understand the rules, you're less likely to mix them up with other rules that are coming. So now, I'm going to take you through a little bit of practice of what those exponent rules were. For number 9, I have the same base, it's 2. And the exponents are 3 and 4. The rule says that I add the exponents when I'm multiplying two expressions with the same base. So this becomes 2 to the power of 7. And if you look at the instructions, use exponent rules to simplify, leave all answers in exponential form with only positive exponents. For the next one, I am multiplying and I have the same base. The rule says that I add them. However, there's another way you could have looked at this. When I add the exponents, 2 plus -8 is -6. And when I have a negative exponent, basically that means change the side of the fraction that you are on, and you are allowed to be positive. And I'm going to continue to talk about that rule and have us get to a better understanding of it. For number 11, when you see t to the 0 power, make your life easy, make it a 1. And then just go, hey, that's it. You could have also added the exponents to get 3. If you have more than one thing multiplying, here we have 3 exponentials multiplying. The same base is there for each one. You're just going to add all 3 exponents together. You have a -4 exponent, a 6 exponent, and an understood 1. If you don't see an exponent, we understand that it's to the 1 power. And then adding this together gives us negative, yes, -3. I'm double checking my arithmetic. but we don't want to leave an answer with a negative exponent. So we write it as 1 over a to the positive 3 power. Uh-huh. Oh my goodness. Thank you. There was a reason I paused when I was adding those numbers because my mind all of a sudden went shuffly. Yes, there we go. Thank you for correcting me. That's very, very important. Okay, next. When I am dividing and it's the same base, they're both b's, I subtract the exponents in the order of the numerator exponent minus the denominator exponent. And this becomes 1 over b squared. Now, I should say right now, if you see a quicker way to get to 1 over b squared, feel free to use that. When it comes to exponent rules, there are often various ways to approach it. For the next problem, it's again division, so I'm going to subtract, but I want to be careful I'm subtracting a negative number. So 5 plus 2 is 7. For number 15, make sure you understand there's the understood exponent 1 if you don't see it. And I subtract my exponents when I'm dividing with the same base. Maybe you saw that without using exponent rules, and if you did, perfectly fine. You don't have to use the exponent rules if you see what's going on from another point of view. With this one, you can either do this. You've got two options. You can go, okay, the numerator exponent minus the denominator exponent, and then try not to mess up. And I'll just stick with this way right now because we're out of time. So that's saying negative 7 plus 2. And if it's a negative exponent, then I write as 1 over the base to the positive exponent. Okay, so that's everything that we need for today. And you can feel free to go. I just want to point out for your homework, we have that first type of problem that I showed you where you just set the exponents equal. We've got some function composition problems. And let me just point this out. This is saying division. So you are actually going to plug 1 into the g function, plug 1 into the h function, and divide those two numbers. And then you're going to use some exponent rules, practice that, and then a little bit more with equation solving. This bit is to review, but save yourself time. If you're still listening to this recording or here in class, you're going to save yourself time. Realize that these are the 3 functions I talked about graphing on day 1. Each of these first multiplies by a number and then does a shifting, a translating, or a movement. Whatever number you see multiplied, multiply the y coordinates by that number, and that will tell you how they change, how those y coordinates change. And then, what?
We were supposed to have a quiz today, right?
You're right. I forgot. That's why I reminded myself at the beginning, but you guys were smart enough to not remind me. Your classmates would have been mad if you did. But let me just point out to you that you need to remember these parent graphs. You can go to the first set of notes to remember those. With this, if you take all the y coordinates and multiply them by -2, that lets you know where they change to. Multiplying by a negative flips something over the x-axis, and then the multiplication by 2 causes those y's to stretch. And then this third one right here is take what you got in B and shift it. And then pretty similar here. Parent graph, multiply the y's by -2, and then do the adding 3. All right. Any questions before you go?